Welcome to the New Books Network.
Welcome to the New Books Network. I'm your host, Gregory McNiff, and I'm excited to be joined by Professor David Helfand, the author of the Universal Timekeepers, Reconstructing History Atom by Atom. The book was published by Columbia University Press in 2023. David J. Helfand was chair of the Department of Astronomy at Columbia University, where he has served on the faculty for nearly 5 decades. He has also been a visiting scientist at the Danish Space Research Institute, the Sackler Distinguished Visiting Astronomer at Cambridge University, and president of the American Astronomical Society, and is currently chair of the American Institute of Physics. He was a founding tutor and served as president and vice chancellor at Quest University, Canada. He has also published commentary in Nature, Physics Today, The Globe and Mail, The Washington Post, and The New York Times, among other publications. I selected the Universal Timekeepers because it offers a thorough and fascinating investigation into how we can use our understanding of atoms to better understand our origins as well as our history. The book is divided into 2 parts. The first provides an overview of the history and current model of atoms, while the second part focuses on using our knowledge of atoms to answer some of the most basic questions of life, including what happened to the dinosaurs, the age of the sun, and what is currently happening to our climate. I should note that the writing is anything but dry, while the humor is definitely dry. One example is Lavoisier's life being cut short by the guillotine. The Universal Timekeepers is definitely much closer to a detective story than any textbook, and will make you appreciate how science can answer some of our deepest mysteries. Hello, David. Thank you for joining us today.
Entirely my pleasure.
David, why did you write the Universal Timekeepers, and who is the target reader?
Well, I've had a somewhat traditional academic scientific career. I've mentored 23 PhD students. I've published hundreds of papers. But my classroom teaching has been devoted to trying to communicate both the wonder of science and the process of science to students who are not going to be science majors. And along the last 49 years, I've made up a few different courses to effect that, and this was one of them.
Can you, as I mentioned in the opening, there are 2 sort of sections to your book, and the first goes through our understanding of the atom and how we arrived there. Could you talk about how we understand the model today for atoms?
Well, it's a particularly opportune time to do that, since this is the year of the quantum, the 100th anniversary of the institution of quantum mechanics, which is our current model of the atom. But the idea of an atom, that is the smallest unit of matter that maintains the properties of the matter, is several thousand years old. Whether it originated in India with Kannada or with the Greeks in 500 BC, it's not completely clear. But the simple hypothesis sounds plausible. If you take a piece of paper and cut it in half, you have 2 pieces of paper, but each one of them maintains the properties that you had to start with. And if you take one of those and cut it in half, and one of those and cut it in half, and one of those and cut it in half again, it's not crazy to think that you might get to a point where you'd have the smallest unit of matter that would still maintain the properties of paper. This idea was promulgated extensively by the Greek philosopher Democritus, who lived about 100 years before Aristotle. It basically lost out for a couple thousand years to the Platonic and Aristotelian ideas that everything was made of 4 basic elements: earth, air, fire, and water, but in fact was resurrected in the 17th century and forms the basis of what we understand the basic units of matter are like today.
When we talk about atoms, we also talk about molecules. Could you just tell us what the difference is there?
So the substances we interact with are manifold. There's millions and millions and millions of different kinds of substances that occur naturally and that we can reproduce in the laboratory. And these substances have specific properties of flammability, of color, of density, of solidness. And those properties are a consequence of the molecules that make it up. Molecules are anywhere from 2 to several billion atoms joined together in a very specific ratio. So the air that we breathe is O2. It's two oxygen atoms joined together to make an oxygen molecule. The wood of the desk that I'm sitting on here is made up of carbon and nitrogen and hydrogen and oxygen in a specific set of proportions. And so all the substances that we think of as making up the world around us are made of molecules, but those molecules are all made of combinations of 94 naturally occurring building blocks called atoms.
You mentioned several times throughout the book, and you remind the readers how small atoms are. Just to give an example, I think you use poppy seeds contain, is it 15 trillion atoms?
Yeah, poppy seeds are about the smallest thing I can pass around a classroom, expect to get it back. And yeah, they contain 15 trillion atoms, which is a completely inconceivable number. So that's the point. And, you know, chemists had the pretty good quantitative measure of atoms 200 years ago, but no one had any clue how big an atom was until 1905, when Einstein, in his Annus Miraculous, his remarkable year, published 5 papers, one of which was on the size of atoms. And that's the first clue we had as to how big atoms were. And they're really, 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 really small.
Fantastic. And the next, or I think a key individual in sort of our understanding of atoms is Niels Bohr. Could you talk about the model he constructed and how relevant that is for us today?
Yes, well, we need to understand why the atoms, these basic building blocks, combine in the proportions that they do. And that has to do with the structure of the atom, which was worked out over the first couple decades of the 20th century. We understand the atom consists of a tiny, tiny positively charged nucleus, which contains 99.9% of the mass, surrounded by a cloud of negatively charged electrons, which balance the charges, so atoms are neutral. But it's the arrangement of the electrons that says how an atom interacts with its neighbors. The atom is 99.999999999% empty space, which is sort of remarkable. You might wonder why you can't pass your hand right through the desk if the atoms are mostly empty space. But the electrical charges are really strong and don't allow that to happen. If I put a tennis ball representing the nucleus of an atom on the outside my building on the corner of Broadway and 120th Street, then the electrons would be orbiting through New Jersey and the South Bronx. So it really is empty space. But it has a very specific configuration, and the arrangement of the electrons in those distant orbits determine how the atom interacts with its neighboring atoms and makes compounds, which we call molecules.
Right. And you talk about sort of the 31 fundamental particles of atoms, and these are particles that are actually inside the atom. Could you briefly talk about that? I know you don't, it's not a major part of the story there, but that includes the protons, the neutrons, the quarks.
Yeah, so our model that I just described, the Niels Bohr model, which has protons and neutrons, two kinds of particles making up the nucleus, and electrons outside, we turned out in the 60s, is not the most fundamental description of matter at the smallest scale. The protons and neutrons are actually composite particles made up of triplets of things called quarks. And as a consequence, in exploring that over the last 50, 60 years, we've come to understand there are lots of individual kinds of particles that exist, some very fleetingly, so you can't buy them in Walmart, but others that are bound up permanently as protons and neutrons. And these make up the fundamental particles of the quantum world. But these are not necessary for understanding the use of atoms as historical observers.
Right. I mean, to clarify, for your book, we're primarily focused on atoms and the nuclei for the purposes of this sort of investigating our history. Is that
That's
fair?
correct. We don't need to go beyond protons, neutrons, and electrons.
Fantastic. What are radioactive isotopes?
So the nucleus of the atom was a great mystery when it was first discovered because it is made up of positive charges. Protons have positive charges, and like charges repel each other. And these protons are packed together in an incredibly tiny space, 10 to the minus 14 meters across. And you'd expect them to have enormous repulsive forces, and indeed they do. So you'd expect the nucleus to fly apart. But there's another force beyond the electric force called unimaginably the strong force. And the strong force is slightly stronger than the electromagnetic force, and so tentatively holds these protons together in the nucleus. However, that alone is insufficient. One also requires some extra strong force, and that's supplied by the other nuclear particle, the neutron, which is neutral, so it doesn't contribute to the repulsive nature of the protons, but it also experiences the strong force, so it acts as a sort of extra glue to keep the nucleus stuck together. Now, the ratio of protons to neutrons is very particular for each kind of atom. The atoms exist from 1 proton up to 94 protons. But the number of neutrons can be very different. For the light elements like carbon and nitrogen and oxygen and helium, the most stable form has the number of protons equal to the number of neutrons. So helium has 2 protons and 2 neutrons, carbon has 6 protons and 6 neutrons. When you get to heavier elements, there's even more of those positive particles packed together, so you need extra glue. And uranium, for example, is uranium-238. That means it has 92 protons and 146 neutrons. So there's extra neutrons for extra glue. Radioactive isotopes are versions of an atom that have a mismatched number of protons and neutrons. So let's use carbon as an example because it's the basis of life and it's the basis of much of what we'll talk about in the future here. Carbon in your fingernail is 99% carbon-12. That is, it has 6 protons and 6 neutrons. 6 plus 6 is 12. But there's a version of carbon that has 7 neutrons, 6 protons and 7 neutrons. And there's another version that has 6 protons and 8 neutrons. 6 protons and 7 neutrons, carbon-13, that's close enough that it's still stable and doesn't fall apart. But carbon-14, 8 neutrons and 6 protons, is just too bad a ratio, and that nucleus is therefore unstable and will spontaneously, without any external influence, fall apart and turn into nitrogen. That's a radioactive isotope.
That is a fantastic description. Building on that, you write in your book that the rates of decay of these radioactive isotopes provide the crucial clocks for our reconstruction history, and that these radioactive isotopes are useful because these decay rates are, quote, completely imperturbable. Can you expand on this, as it seems like a key theme of the book?
It's absolutely critical to using these isotopes as clocks to reconstruct history. So it turns out that this process is, as far as we understand it, and that's over the last 100 years of the quantum understanding here, is a completely random process. This is very disconcerting to some people. Einstein, for example, never accepted this. He thought there must be some hidden variable that we just didn't understand yet. But every experiment we've done and every theoretical calculation we've brought to bear suggests that it is truly a random process. And it's imperturbable in that you can heat it to 1 billion degrees, or you can freeze it to absolute zero. You can hit it with a hammer. You can put it in a magnetic field. No matter what you do, you cannot change the rate at which these radioactive nuclei randomly, spontaneously fall apart. A key feature of this is that every individual isotope of each kind of atom has its own what we call half-life. So if you flip a penny, you get a head or a tail. There's no other option. If you flip another penny, you get a head or a tail. There's no other option. And if you do this 10 or 100 times, you'll get roughly 50 heads and roughly 50 tails. So the same thing is true with radioactive decay. In fact, I do this in class. I have all the students stand up and flip a coin, which it turns out 18-year-olds don't know how to do anymore. I guess because they don't use coins. But half of them get tails and they have to sit down. And then they flip again, the ones that are still standing, and half of them sit down. So after 2 flips, you have a quarter of them left. And then they flip, and after that, half of them sit down, so 1/8 of them is left. And that's exactly what happens with a radioactive sample. You start out with a whole bunch of nuclei, and even though the typical half-life, the time it takes for that typical proton to decay, nucleus to decay, could be, in the case of carbon, 5,730 years, one could go off in the next minute if you have a big enough sample. And so by counting the number of original isotope numbers to the number of products after the decay, that ratio tells you how old the substance is.
You mentioned in the book this average lifetime definition is only an average and that these formulas are probabilistic. Is that what you're referring to there with the coin toss, the idea that we don't have the specific understanding of when or how it would decay, but it would follow some kind of maybe Gaussian or bell curve? How do you think about that?
We know how it decays because we know it transforms a neutron into a proton or a proton into a neutron and spits out a particle or an antiparticle. Each one has a specific decay mode, and we understand what those are. But we cannot predict quantitatively. We only can measure in the laboratory what the half-life is. And the half-lives range from a tiny fraction of a second up to 100 times the age of the universe. So there's an enormous range of half-lives depending on that ratio of neutrons to protons. In the case of carbon, which we'll discuss a lot, I guess, it's 5,730 years. So if you start out with 1,000 carbon-14 isotopes, then after 5,730 years, you'll have 500. And after another 5,730 years, you'll have 250. And after another 5,730 years, you'll have 125. The little atoms have no memory. They don't know when you started watching them. They don't know when they were supposed to decay. They just know that in one half-life, they have a 50% chance of decaying. And if you have a big enough sample, that's what it'll reflect.
That makes sense. Once you lay out this model for how atoms work and how isotopes decay, the book shifts to several use cases that, as you say, help us reconstruct our history and understand our origins. One of the first sort of investigations you present is determining the authenticity of artworks. Could you talk about an example there? I know you cite a few at either the Met or maybe the Morgan Library.
Yeah, so this is a fascinating use of this technique. We want to examine what a painting is made of without actually touching the painting, without scraping some painting off. Because if you have a 15th century painting, you don't really want to scrape off a corner of it to take it to the chemistry lab and figure out what's there. So one technique is to irradiate the painting with neutrons from a nuclear reactor or with X-rays or protons. And in doing so, we can excite the nucleus of the atom, and as it decays, it emits light X-rays of a very specific wavelength that's unique to that isotope. And so we can inquire millimeter by millimeter across the painting what atoms are present in the pigments that were used to make the painting. Now, pigments have developed a lot over time, from caveman times to modern times. And so different pigments are made of different atoms. They're made of compounds of different atoms. And for example, there is a famous forger called the Spanish forger who produced hundreds of works of medieval art. He's called the Spanish forger because he was originally attributed to Inglese, who was a Spanish painter in the 1400s. But in fact, we believe he worked around 1900 in Paris. And I say he because we don't know who it is, so it could have been a she. And they produced several hundred of these, which are in museums all around the world. In fact, there's so many of these forgeries that the museums actually have shows that just have the forgeries in them. And we know they're forgeries because we can inquire of the pigments in the paintings by irradiating them this way and looking for what comes out. And we find pigments that simply didn't exist until the 19th century, or in some cases until the 20th century. And so this is a guaranteed way of deciding which of these paintings are forgeries and which are real.
You talk about I think, a Book of Hours, which contains copper arsenic. And from that, and using how we can determine the decay time of arsenic, that helps us determine the authenticity of the book or date it.
Well, no, that's the interesting thing about the Spanish forger. He or she was very clever. They used original 14th, 15th century manuscripts, wood blocks, vellum. So the material out of which they're made are originally from that period of time. So dating-wise, it looks like it's real. But when you irradiate the pigments and let them decay, that is, spit out their signature X-rays, you can tell what's there. And this arsenic-laden green paint, turns out, was first invented around the beginning of the 19th century. In fact, there's a funny story that goes with that. Napoleon was, of course, ultimately exiled to the St. Helena in the Atlantic Ocean. And he loved this color. It was the deep, deep green. It's called Paris green, as a matter of fact. And when the autopsy was done on Napoleon, it was discovered that he had arsenic poisoning. And we don't know if he was eating the paint chips off the wall or whatever, but it was that arsenic-based green pigment.
Interesting. Moving on to carbon dating, and in this chapter, you talk about the inventor of carbon dating, Willard Libby. Could you talk about how carbon dating works and how we use accelerated mass spectrometers today?
Sure. So anything that was alive, a plant or an animal that eats plants or an animal that eats animals that eats plants, has carbon that was derived from the environment when the plant was growing. Plants are just devices to suck carbon dioxide out of the air, that's CO2, use sunlight to break the bond between the carbon and the oxygen so it breathes out the O2, which is nice for us because that's what we breathe in. And the carbon goes into building the cellulose and the sucrose and the fructose and the molecules that make up the plant or the fruit of the plant. While the plant is alive, it's breathing in CO2, most of which is carbon-12 O2, some of which, 1% or so, is carbon-13 O2, and a tiny, tiny fraction, 1 in a trillion molecules, is carbon-14 O2. So the plant has that standard ratio that was in the air represented in its stem and in its fruit and in its roots and in its leaves. As soon as the plant dies, however, of course, it stops breathing in carbon dioxide. That's what we mean by a dead plant. It's not doing it anymore. And the carbon-12 and carbon-13 remain there forever because they're stable. But the carbon-14 is decaying. And so after 5,730 years, there'll only be half as much left as it was when you started. Now, we don't have to wait that long. You can wait 100 years, and there'll be a little bit less, and you can calculate exactly what that was because it's a simple mathematical equation. And so anything like, for example, the Shroud of Turin, which was supposedly the burial cloth of Christ, which is kept in the Turin Cathedral still in that role, was in fact painted in 1347 by a corrupt local priest who wanted to make money off the pilgrims who would come and touch the burial cloth of Christ. And we knew this actually historically from written records, but of course most people ignore written records. And so we finally took a tiny, tiny sample of this linen cloth, linen coming from flax, which used to grow in a field, and dated it, and lo and behold, it was dated to 1350 plus or minus 20 years. So that's how we do it. And we can use this to date things from a few decades old to maybe 50 or 60,000 years old. After that, so much of the carbon is decayed away, there's not enough to make measurement. Now, when Willard Libby did this, he actually sat there and waited for the carbon-14 to decay, or probably had his graduate student do this. And you counted, every hour there'd be one to decay, or maybe it would be 2 hours until there's a decay. And you waited for weeks and weeks and weeks until you'd accumulated enough, and you figured out what the decay rate was. Now we have a much simpler and more sensitive way of doing it by using a mass spectrometer, by which we vaporize a little bit of the material, and then we literally sort it atom by atom, in fact, isotope by isotope, into buckets depending on its mass. And it's a fairly straightforward process to do. So we can literally count the number of carbon-12s and the number of carbon-14s and just take that ratio, which immediately yields the age.
One of the more interesting chapters is how you discuss how researchers are able to use isotopes to construct our ancestors' diet, particularly corn or maize, and how it sort of originated in Mexico and ended up in New England via indigenous populations. Can you talk about how they made that discovery? And I think particularly Anna Roosevelt was key to that discovery.
She didn't work on that discovery. She worked on an analogous discovery, which I can mention. So this is a great example because it uses carbon-12, carbon-13, and carbon-14. So as near as we can tell from genetic analysis, maize, what we call corn and the rest of the world calls maize, was produced from a plant called teosinte, which is a grass that grows native to Mexico, south of Mexico City, the mountains south of Mexico. And we believe and it has 2 or 3 little grains. I mean, you wouldn't confuse it for an ear of corn today. But it was nutritious. And so the local indigenous peoples learned to crossbreed things then. This is not a new idea. They were doing it 8,000 years ago. And by 6,000 years ago, they were cultivating corn. But that's in 5,000 kilometers away from New England, right? So what happens? Well, it turns out that maize is an unusual plant. Most plants developed over the last several 100 million years a process of photosynthesis which begins by joining 3 carbon atoms together. Corn and a few other grasses like sorghum and sugar cane and things like that have developed much more recently in evolutionary history, maybe 50 million years ago. And they start by 4 carbon atoms together. Now, it turns out that the process by which this occurs is a very impatient process. So it wants the speedy molecules to put together 3 carbons in a row and get the process of photosynthesis underway. And the speediest molecules are the C12O2 molecules because they weigh the less. I've run 6 New York City marathons, and now I weigh a lot more, and I know I'm a lot slower. So the slow molecules are the carbon-13, and the even slower molecules are the carbon-14. The C4 plants, though, the ones that take C4 carbons in a row to start, have to be a little more patient because they got to wait for 4 to show up. And so they discriminate less against the slower carbon-13. So all you have to do, since carbon-12 and carbon-13 are totally stable, is look at the bones, because you are what you eat atom by atom. Look at the bones of a culture and measure their age with carbon-14, because you know from the dating technique I just described how that works. And then look at the carbon-13 to carbon-12 ratio. And what you see is a sudden, usually over 100 years only, transformation of a diet based solely on the 3 carbon plants, because that's what grows in temperate zones around the world, to a diet that's 70% 4 carbon plants, that is corn. Because not only did the Indians eat the corn, but the deer ate the corn, which the Indians ate, and the chickens ate the corn, and the eggs had the carbon-13 to carbon-12 ratio representative of corn rather than representative of blueberries or whatever else was growing around. And so we can do this by going all the way from Mexico to New England and see as the corn agriculture progressed with time, such that by about 2,000 years ago in upstate New York, they were growing corn and their diet had shifted from a C3 plant to a C4 plant.
And just on that point, a related point, I believe Anna Roosevelt had a thesis about maize being introduced 2,500 years ago, and at the time may not have been completely accepted, but over time.
Yeah, so she was working in the Orinoco Valley in Venezuela, and through standard anthropological techniques had determined that the size of the chiefdoms there 2,000 years ago was much bigger than could be supported by just digging up manioc roots, which is what the standard system was. And finally, by measuring the bones carbon-13 to carbon-12 ratios, show that corn was actually introduced nearly 1,000 years earlier than standard archaeological wisdom had suggested, and that's the reason. Corn has a lot of protein for a grain. It's the most protein-rich grain, and so it provides protein and carbohydrates both. And so it's very valuable, and that explains the size of the chiefdoms.
Yeah, probably the most amazing, there are several amazing facts in your book, but one thing that's just, again, fascinating is how researchers were able to map the weekly, and correct me if I'm wrong there, the weekly location of a mammoth, which lived in Alaska over 17,000 years ago, by analyzing the isotopic ratios in the tusk.
Exactly.
And they were able to do that just by examining these ratios that you talked about between the elements.
Yeah, I found this amazing too, and this got added at the last minute because it was only done a couple of years ago, just about as the book was about to come out. I said, I have to put this in. This is just too good to be true. So 17,100 years ago, there was this baby mammoth that was born in Alaska, south of the Brooks Range. And the baby mammoth started eating. And the baby mammoth is what it eats, just like we are. And so the isotope ratios, particularly the strontium isotope ratios. Strontium is a mineral that's found in the rocks, which means it's found in the soil, which means it's absorbed into the plants, which means it's absorbed into the bone structure because it's analogous to calcium in the periodic table. And so you have strontium in your bones from the diet that you eat. This mammoth wandered around Alaska for the first 12 or 14 years with its mother, just like modern elephants. The young males stay around for about 12 or 14 years, and then they go off on their own. And because the landscape is well geologically mapped, and you know what the strontium and rubidium element ratios are in these rocks, you know where the mammoth was eating in a given day. We also have oxygen isotope ratios, nitrogen isotope ratios, and carbon isotope ratios. And we can see this mammoth sticking near the southern part of Alaska for much of its time. We can see it even migrate season by season, going south in the winter and north in the summer by the oxygen isotope ratios, how far it was from the ocean. And we can make a map over the 28 years of the mammoth's life as to where it was week by week by examining along the tusk, which just grows continuously from the time it's born. So the tip represents what it was like when it was born, and the part attached to its jaw is when it died. And we even know how it died. We knew it got stuck north of the Brooks Range, and it died from starvation. We know from the nitrogen 15 to nitrogen 14 ratio, because your body normally excretes nitrogen 14, preferably over nitrogen 15, again, because it's lighter, so it moves more easily. And therefore, your proteins are made more of nitrogen 15. And you can see the nitrogen 15 to nitrogen 14 ratio skyrocket in the tusk of this mammoth in the final few weeks of its life because it was digesting its own proteins because it had run out of food in the winter north of the Brooks Range. So it's just a fascinating story about how one can reconstruct the details of life far before there were people to record it.
Yeah, and at that level of precision, I mean, weekly, that's just amazing. Moving to a topic that I think is front and center these days is the climate. You talk about a number of models, and one's going back tens of thousands, and even I think 450,000 years. But you conclude it isn't so much the amount of carbon in the atmosphere; it's the rate of change in our atmosphere. Can you explain how we determine this rate of change and what models we're using to get there?
Yeah, well, here we don't need models. We can just take direct observations, at least until this week we could. So in 1958, a geophysicist called Charles Keeling decided it might be a good idea to measure the carbon dioxide content in the atmosphere over time, just to see how it changed. And so he set up an observatory in Mauna Loa in Hawaii, and just every day took a sample of air and literally, using a mass spectrometer, counted the number of CO2 molecules and the number of oxygen molecules, number of nitrogen molecules, etc. And the answer was out of every million molecules of air, about 312 were carbon dioxide. Now, he continued this over time and found, first of all, that the Earth breathes in and out once a year, as in the Northern Hemisphere summer, when it's breathing carbon dioxide out of the air, the carbon dioxide ratio goes down. And then when it's rotting in the wintertime, that carbon dioxide goes back into the atmosphere. And so there's an annual cycle that goes up and down. But what's much more striking when you plot the data from then till now, 70 years later, is that the amount of carbon dioxide has been steadily increasing, such that I looked it up yesterday, was 427.8 parts per million. So nearly 50% increase over just 60 years. Now, why is this significant? We have records, again, no models involved. We have records going back 450,000 years from tiny bubbles that are captured in the ice of Greenland and Antarctica. So the layers of Greenland and Antarctic ice are both nearly 3 or 4 kilometers thick, and they represent a history of the last several 100,000 years of the Earth's climate, because every year it snows, traps some air in little bubbles. You go in your refrigerator, you look in your ice cubes, you can see little bubbles. Those are little samples of air. So it's just like we had a chemist there with a little ampule who could take a sample of the atmosphere and plug it up for us and label it. This was 27,432 years ago. And so we have a continuous record going back that far, and we can see how much carbon dioxide there was in the atmosphere over that period of time. And it's small and variable, but not nearly by the amount that we've seen in the last 60 years. Now, going back further, we have records in coral reefs and deep sea sediments and things like that that show 50 million years ago, there was much more carbon dioxide in the atmosphere than there is today. And we can see that event happening over geologic time. But it happens, the kind of change we've seen today on the time scale of 60 years happens on the time scale of 10 to 20,000 years. And the Earth's climate system can adjust on that time scale. It cannot adjust on the time scale of 60 years. We furthermore use the carbon isotopes again to show unequivocally that the increase in carbon dioxide over the last 60 years has been a consequence of burning fossil fuels. Because fossil fuels are made of the remnants of plants from the Carboniferous era 300, 400 million years ago. And while they still have carbon-12 and they still have carbon-13, because those are just plants like plants today, they have no carbon-14 because in 5,000 years, half decayed. In 10,000 years, 3/4 is decayed. And in 300 million years, there is zero left. And we can actually chart over the last 50 years the steady decline of the carbon-12 to carbon-14 ratio, or carbon-14 to carbon-12 ratio, because we've been adding to the atmosphere this carbon dioxide that comes from burning fossil fuels with no carbon-14 content. And so it is an unequivocal fact that human burning of fossil fuels has produced at least 85 to 90% of the carbon dioxide that appears in the atmosphere, and the carbon dioxide in the atmosphere has increased at a rate more than 100 times faster than it has in any time in geologic history. As we can measure this today, but maybe not beyond today, because the Department of Energy recently announced this week that we're going to stop measuring carbon dioxide in the atmosphere at all 5 observatories the U.S. uses to do that. I guess the hypothesis is it's just better not to know.
I'm reminded of the Simpsons episode where, in order to prevent the meteorite crashing on the planet, they destroy the telescope. So maybe I'm all find. You answered the question, but the C12 to C14 ratio is actually declining, and I think you estimate fossil fuels are 85% roughly of this rise in CO2 over the last 60,000 years or so. Is that correct?
That's right. It's 85 plus or minus 5%. The rest comes mostly from burning forests. Now, forests, of course, are alive before they're burnt, and therefore have a carbon-14 to carbon-12 ratio characteristic of the atmosphere today. And so some of it is contributed by that.
And I believe in the book you said we're at the highest level of CO2. Is it in the past few millions of years, or where do we?
We have good records going back 10 to 15 million years, and we're higher than any time then. As I say, before that, the CO2 level was much higher than it is today. But the Earth was a very different place. There was no ice on the Earth. There were palm trees growing in Greenland. And the whole ecosystem was completely different.
Yeah, I'm sure you've been asked this before, and I realize this might be slightly outside the scope of the book, but in terms of time, do you have a sense for, how much longer, or how should we think about, reaching the point of no return? Is there an inflection point? Obviously, we want to change our behavior soon, but, how do you think about that when we can really start seeing the effects of this?
People talk about tipping points a lot. I'm not convinced, I'm not an expert in this, it's not what I study. I'm not convinced there is a single tipping point. But what we do know is that the carbon dioxide we put in the atmosphere today stays there for 3 or 4 or 500 years. So there's not going to be any natural rebound, even if we stop doing carbon dioxide completely tomorrow. And now the methane that we put in the atmosphere, which is the second most important greenhouse gas, has a residence time that's only measured in decades, maybe 30 or 40 or 50 years. And so changing our habits of dumping methane into the atmosphere would have more of an immediate effect. But the current trajectory is that we are putting the net sum of greenhouse gases into the atmosphere faster this year than last year, faster last year than the year before, and there's no obvious sign of turning over. And that inevitably is going to lead to increasing Earth temperatures and all the things that follow from that.
Yeah, no, it really was striking and alarming, that chapter, and the like I said, the charts you show. I know you talked about the records, but just the variability in carbon levels over thousands or tens or hundreds of thousands of years was really fascinating. Speaking of fascinating, I think one case that every 10-year-old boy at least would appreciate is how the geologist Walter Alvarez determined the cause of the dinosaur extinction almost to a level of precision, again, that would rival that mammoth, I think 66.04 million years ago. Could you talk about how he determined A, the cause of the extinction, and B, the time frame?
Yeah, he determined the cause. He didn't determine the time frame. Someone else did that. But yeah, that level of precision, just so people have an understanding of it, it's like me walking into a room, looking at you, and being able to tell when you were born to within a week, which, needless to say, I can't even do to within 5 years, let alone a week. So it was known from the middle of the 19th century that there was an abrupt change in the fossil record of sea creatures around 66 million years ago. They didn't know that number yet, but there was a specific strata in the layers of rocks that contained fossils where there was an abrupt change, and this was written about in 1860. So that's been known for a long time, and it's currently called the Cretaceous-Paleogene boundary, and it's a well-known thing in geology. What Walter Alvarez did was he measured the isotopes of various atoms, several dozen atoms, below, at the boundary, and above the boundary, and compared them. And I think there were 28 different atoms measured. 27 of them were just smoothly across the boundary, no change, nothing happened at the boundary. But iridium-193 jumped by a factor of 30 right at the boundary. Now, iridium is a heavy element, 193 atomic mass units, and therefore, like gold and platinum and the other elements in that range, sunk to the center of the Earth when the Earth was formed and was still hot enough that it was liquid, and all the heavy nuclei sink to the center of the Earth. So there's a lot of gold in the center of the Earth, which we're never going to access, but it's there. It's rare on the surface. Iridium is extremely rare on the surface, and the only place it comes from is meteoritic dust that rains into the atmosphere at the rate of 10,000 tons a day or so throughout history. So if it's raining in at a steady rate, you'd expect a steady amount of iridium every centimeter you go up the rock face. Here you found right at this boundary where the fossil layer changes, there was a 30-fold increase in the amount of iridium. And the source of iridium today is from asteroids. And so the hypothesis was an asteroid must have collided with the Earth to provide this iridium. I might think, well, if he found this in Italy, then did the asteroid hit Italy? And the answer is no. He also found it in Denmark and also found it in New Zealand. Because when an asteroid that's big enough, in this case about 10 kilometers, 6 miles across, hits the Earth, it makes a real mess. This has happened in the past, and it's going to happen again, most likely. Hopefully not too soon. But it throws thousands of cubic kilometers of material that's been molten because of the huge energy of the impact into the atmosphere, which spreads around the entire Earth. And as a consequence, has a major impact on life, in this case, killing all the plant life. And if you're a brontosaurus that needs to eat half a ton of plants a day to stay alive, you don't live very long.
Yeah, I think you're talking about the dinosaurs being unlucky, so to speak, in the certain regions with anhydrite, if I'm pronouncing that right, which contains sulfur acid, and really just dramatically change their ecosystem and their environment. But I guess the plus side is it allowed furry little creatures then to evolve into us today, or hopefully there was some silver lining to that.
If we're considered a great success, yes. So So yeah, that's exactly what happened. 75% of all species on land and in the ocean died, down to single-celled organisms in the ocean. I mean, it's not just giant things that died, but the furry little creatures, the little mammals, which had existed for tens of millions of years before that, but it had completely been subservient to the dinosaurs in the ecosystem, now had the whole ecosystem to themselves. They could survive a few weeks of nuclear winter, which is what this was, and then emerge and evolve over the last 66 million years to produce us.
Yeah. Well, yeah, I guess there's a silver lining there. One interesting fact, I believe it was Walter Alvarez's father, or Walter Alvarez, you presented Columbia this theory in like the 1980s. Is that right, on his theory of the dinosaur extinction?
Yeah, so I remember this vividly because it was an interesting incident in the sociology of science. So I got to Columbia in the 1970s, and there were 4 Nobel laureates and several people who had worked on the Manhattan Project in the department at the time, very distinguished group of people. And they always sat in the front row for the colloquium. Yeah. This was 1980 when they came up with this hypothesis. And Louis Alvarez, who is Walter Alvarez's father, was a famous physicist, also Nobel laureate at Berkeley. And it's a real interesting question as to whether this paper ever would have gotten published if Louis Alvarez's name hadn't been on it, because Walter Alvarez was just a young postdoc. In any event, Louis came to give the talk, not Walter. And Louis gave the talk and said that he was convinced that an asteroid had killed the dinosaurs. And all of the Columbia bigwigs were walking out, sort of shaking their head. God, it's really sad when really smart people lose it, near the end of their lives. And I just thought this sounded really good to me. I mean, it had data, right? He had data. He measured the molecules. He measured the atoms, isotopes across the boundary. I thought it was a great idea.
Yeah, no, that would have been a fascinating talk to sit in on. Moving on and, getting to dating to a level of precision, I think you talk about the ratio of rubidium to strontium, allowing us to date the age of the oldest meteor and thereby determine the life of our planet. Could you go into a little more detail there?
Yes, so rubidium is a radioactive isotope, but it has a really long half-life, like 49 billion years, which is like 11 times the age of the universe, and 11 times the age of the Earth. It's several times the age of the universe. So you might think, gee, well, nothing must have decayed, but, these atoms are really small, and there's lots of atoms. And so occasionally one will decay. And rubidium-87 decays into strontium-87. There's also, however, a stable isotope of strontium that doesn't decay from anything, called strontium-86. And if one takes the appropriate ratios of strontium-87, rubidium-87, and strontium-86, one can make an estimate of when the minerals involved in the strontium were coalesced. And we do this to meteorites because they're the most primitive stuff in the solar system. They came even before planets. And as a consequence, again, we can get a number to 4 significant figures, 4.567. I like that because it's 4567, so you can remember it easily. 4.567 billion years ago is when the solar system first coalesced out of the cloud of interstellar gas from which it was born.
I just want to cite another fact. In your discussion of stars, you talk about certain stars that have a mass several times greater than our sun. And when the energy to counter the gravity is no longer available, I think it inevitably that explosion, quote, releases more energy in 1 second than the sun will in 11 billion years. That just seems unbelievable.
Well, it makes a real mess. It's quite an explosion.
No, I was just saying in the book, I think you say, yeah, this is probably an explosion. And I think that's probably right. I know the study of your book, the topic isn't focused on neutron stars, but it is one of your areas of specialty. And in the book, you talk about them being remarkable, and you also discuss a discovery about the creation of heavy elements in neutron stars. Could you talk a little bit about that?
Yeah, so you were talking about the exploding stars before. The exploding stars systematically build hydrogen to helium and helium to carbon and carbon to nitrogen, nitrogen to oxygen, oxygen to magnesium, et cetera, building their way up to iron, which is number 26 in the periodic table. And the reason that's crucial is because they do this by the process of fusion, that is sticking nuclei together. But iron is the most stable possible arrangement of protons and neutrons. 26 protons, 30 neutrons. And as a consequence, if you try to add something to it, it becomes less stable. Up to that point, if you add something to it, it becomes more stable. And so if something becomes less stable when you add something to it, that means it absorbs energy rather than giving off energy. And so that's what causes this catastrophic collapse of the star and the explosion that follows, because it tries to go from iron 56 to cobalt 56 to nickel 56, and it sucks energy out of the center of the star, so gravity collapses the star. And it blows up the star. Now, there's lots of energy there, huge amounts of energy, as you said, 1 second, the sun's time energy output. And so we've always sort of waved our hands a little bit and said, well, that's where all the other elements are made, right? Because there's 60 other elements beyond iron, 70 other elements beyond iron 56. But quantitatively, we've never been able to demonstrate that very successfully. What we discovered just in the last few years is that neutron stars may be responsible for many of these very heavy elements. Neutron stars are remarkable. They are a macroscopic object, say 10 kilometers or so across, with the density of an atomic nucleus. So a single teaspoonful weighs 1 billion tons. So it's like all the cars, trucks, and SUVs on the planet compressed to the size of a sugar cube. And normally we can only study this inside the nucleus of an atom, which is really small and hard to find and hard to study. But here we have macroscopic objects that are sitting out there in space, spinning around, giving off energy, showing us their locations. And as a consequence, we have lots of nuclear physics we can study there that we can't study in the laboratory. Now, it turns out that my office mate in graduate school and my thesis advisor set out on a project to find a binary neutron star, that is, 2 neutron stars orbiting each other. Turns out the sun is typical in almost every respect except the fact that it doesn't have a companion. Most stars have companion stars. And it's possible that one of these supernovae blows up and leaves a neutron star behind, and then the other supernova blows up and leaves a neutron star behind, and you end up with 2 neutron stars orbiting each other. And if that happens, because they're so incredibly massive and so incredibly dense, they will give off what's called gravitational radiation. That's fundamentally different than the electromagnetic radiation we observe the rest of the universe in. It's actually ripples in the fabric of space-time itself. And if they give off this radiation, their orbit should decay because they're losing energy. And so they should spiral together. And my office mate and thesis advisor demonstrated this was the case with the binary neutron star they discovered, and so indicated the presence of gravitational waves. But that's an indirect measurement. It's an inference that the reason the orbit is decaying is because of gravitational radiation. About the same time they won a Nobel Prize in 1993, the Laser Interferometry Gravity Wave Observatory was proposed and started to be built in 2 stations, Washington State and Livingston, Louisiana. And the idea there was to detect directly the ripples in the fabric of space-time from these kinds of events. And indeed, in 2017, they discovered an event in which 2 neutron stars merged together in a matter of a fraction of a second, gave off a burst of gamma rays 2 seconds later, which was detected by a satellite in space, and therefore found optically as a bright burst, first of blue light and then of red light, exactly according to what we would have expected to happen in this instance. And the light analysis of the light signal from this event indicates that it's the source of many of the heavy elements in the periodic table. So that solved a long-standing mystery. We don't need to wave our hands about supernovae anymore. We know merging neutron stars produce the heavy elements.
Excellent. Towards the end of the book, you obviously look into the origins of the universe. How far back can we go to the creation of the universe with our understanding of atoms?
Well, the direct observations go back to 390,000 years after the universe's birth. The universe is 13.81 billion years old. So going back to 390,000 years may sound like a lot, but it's really, really a baby picture of the universe, like when a baby is a month old or a week old compared to a full-grown adult. And so we can actually see what the universe looked like then. The cosmic microwave background shows us exactly how matter was distributed in the universe at that time. However, we can infer what went on far before that because it's just atoms, and we understand atoms really well. And if we take the ratio of heavy hydrogen to hydrogen and hydrogen to helium and lithium to hydrogen, we can infer the temperature and the density that the universe must have had in the first 3 minutes when it was making the first hydrogen and helium nuclei, and going on before that in the first millionth of a second when it was first coming together with protons and neutrons as separate particles. And in principle, we can go back further than that, although the physics gets less consistent with what we've already been able to do. But easily we can go back to a millionth or probably a billionth of a second and describe the conditions of the universe that led to us today, who can infer what the universe was like then, which is a fairly remarkable fact.
Yeah, I was about to say, that's just absolutely amazing. We can get to within a millionth of a second of this singularity. I do have one random question for you. You talk about the isotope thorium-232 having a lifetime of 14 billion years, which is slightly or somewhat approximate to the universe being 13.8. And does that help us at all with, I guess, confirm independently, like the cosmic microwave background support for the life of the universe? Just curious if there's anything unique about the lifetime of that isotope and our dating of how old the universe is.
Well, you're right. The lifetime of that universe is very close to the lifetime of that element is very close to the lifetime of the universe. But the answer is no. And the reason was there is no thorium-232 when the universe is born. In fact, there's only hydrogen, helium, and lithium when the universe is born. And while the first generation of stars could indeed make heavy elements, as we know the stars make heavy elements, the first generation of stars is very different than the stars that exist today because they had no carbon, nitrogen, oxygen, iron, magnesium, silicon, etc. And so we believe they were much more massive, hundreds to maybe thousands of times the mass of normal stars, and therefore would have evolved very differently. And the end of their lifetime is a somewhat debated topic. But the point is, we would need to know the amount of thorium-232 and the amount of radon-228 that it decays into, and then the ratio would tell us the age. But since there was no thorium nor radon then, and we can't even predict theoretically how much of each of those stars would make, it doesn't provide another check on the number.
There you go. Thank you. That concludes our interview. I should say, in addition to being a wonderful researcher and scholar, Dr. Helfand is also a great educator, has won numerous awards for his teaching. So I highly suggest you buy the book, join your local astronomy club, and invite him to give a talk. He has graciously to do that for several talks in the New York area, several clubs in the New York area. Again, the book is The Universal Timekeepers, Reconstructing History Atom by Atom by David Helfand. Thank you very much today for joining us, Professor. Really enjoyed the conversation.
It's been entirely my pleasure.